Hi there. Sorry guys, for starting a bit late. Um, so yeah, it took me a bit longer to make dinner, and now I'm finally live, and let's get started. So today we will continue looking at Markushevich's text on complex variables, and we're last time it was like motivation, why complex variables is needed, and what sort of results are ahead. So last time, a central message was that complex analysis was interesting because it is possible to derive sometimes highly non-trivial global properties of a function just from local information. But today, well, of course, it's going to be mostly a review of the complex numbers, as well as some topology of the complex plane, things like convergence, open and closed sets, that kind of stuff on the complex plane. Okay, so and if we have time, we will do some exercises. But just because Markushevich's original text does not come with exercises, because it's called a short course, in the theory of analytic function, we will use a Western counterpart. That's Brown and Churchill, a classic text as well. Lots of exercises, very approachable. So if we have time, we'll do some exercises from there. Anyway, without further ado, let's get started. So our study for today is complex numbers and its geometric interpretation. So complex numbers and their geometric interpretation. Okay. Usually the theory of complex numbers is usually presented in advanced algebra in high school. So here we'll only recall the main definitions and results, and perhaps augment them somewhat in the future exposition. So each complex number C has the form a plus ib, where a and b are real numbers. So this is a general element in the set of complex numbers, which is denoted as this double strike C notation. A and b are real numbers. Yeah. And I is the so-called imaginary unit. Regarding the meaning of I already made a video, actually a month ago, on demystifying this symbol. Okay. So for centuries, I was viewed with suspicion because somehow I squared is -1. Of course, there's no such thing in the set of real numbers, so that's why it's called imaginary. It was a name given by Descartes as almost as a derogative, to simply dismiss it as not real mathematics. But I is very much real. Not in the sense of a real number, the technical sense of real number, but the thing is, it is no less real or imaginate or more imaginary than the real numbers. You can construct them. You can construct complex numbers. You can construct real numbers. Okay, so this is unfortunately a historical baggage. Even to this day, thanks to the terminology, beginners find seem to have this weird feeling that this is somewhat less real than, say, the real numbers. No, complex number is just as valid as real numbers. And so I made a video about months ago explaining the process through which we demystified. Hi, Steve. The process through which we demystified the complex numbers. throughout centuries. I'm not going to repeat myself here. Instead, we're just going to take a more computational approach and just consider a plus ib as it is without worrying about, okay, what this actually means. But if you're interested in the foundation of complex numbers, I strongly recommend you check out that video and why it was introduced historically and how the story from the algebra and the geometry side complement each other. Okay, so I is called imaginary unit, and A is called the real part. Okay, the real part of C. Okay, and B is called the imaginary part. Imaginary part. Okay, and two complex numbers are equal if and only if their real part and imaginary part matches. So C equals C prime if and only if the real part of C equals the real part of C prime and the imaginary part of C equals the imaginary part of C prime. Okay, if imaginary part is 0, if the imaginary part of C is 0, we say that C is real. And so if the real part is 0, we call C is purely imaginary. Now, these are just terminologies, okay? Purely imaginary. Okay, so to interpret complex numbers geometrically, we assign to a plane coordinate axes, rectangular coordinate axes, like this, and consider each point in the plane. The points say x and y with coordinate x and y. Consider this point as the image of the complex number z equals x plus iy. Equals x plus iy. So now you have a one-to-one correspondence between the plane, points on the complex plane in a rectangular coordinate system, and a complex number. Okay, so this condition uniquely relates the set of all points in the plane and the set of all complex numbers. And we usually also denote or draw a vector starting from the origin to xy to represent the complex number as well. A point, a vector, they can all represent a complex number. So the set of all real numbers is represented by the x-axis, which is called the real axis. The real axis. The set of all imaginary numbers is represented by the set of points. The set of all purely imaginary numbers is on the vertical axis. So this is called the imaginary axis. More terminologies. All right. So chances are you already seen this stuff. This is just a review of what's usually taught in algebra. Okay. The plane, except at the origin. Okay, except at the origin, all the numbers on the points on the imaginary axis are purely imaginary, except the origin. So the plane as a whole is called a complex plane. It's also called Gauss-Argand plane or Gaussian plane. There's a bunch of names. So this is the complex plane, aka Gauss-Argon plane, and or Gaussian plane. So historically, this was the first step towards demystifying complex numbers. So once people started to regard complex numbers as points on the plane, it started to feel less mysterious. Okay, and often we also call it the z-plane. For example, if a variable, often we write f of z, right? F of z as a complex function. So depending on which variable you're talking about, if the variable is z, we also call this the so-called z-plane. So z is usually the independent variable in complex analysis, whereas w is the dependent variable. Okay, so often we will draw two complex planes to indicate a mapping between two planes. So from z-plane to w-plane. Hi, Wendell, and thank you very much for joining the stream. Okay, so from now on, the complex number x plus iy and the point x plus iy will be used synonymously. Okay, awesome. So let's continue with this diagram. We can define, for example, the length of the vector and as well as the angle it makes with the real axis. All right, so for the geometric interpretation, z equals x plus iy, aside from the point, the xy, or aside from the Cartesian coordinates xy, we can use a vector whose projection, aside from the point xy, we can use a vector whose projection on the coordinate axes are x and y. Let me just draw the projections. All right, so this is x, this is y. And the beginning, okay, sorry. So for this reason, we're going to use the terms complex numbers and vector also interchangeably. So x plus iy can be treated as a point as well as a vector. Okay. The length of the vector is called the modulus. So the length of the vector, which is this part, which is this thing, okay, this is the length, which we write as z modulus. Looks like an absolute value, and indeed it is a generalization of absolute value in a set of real numbers. So this is called the modulus. This is defined as the square root of x squared plus y squared, simply the length of the vector. And here, this angle right here, the angle between the positive real axis and the vector is called the argument. And here we assume that the z is non-zero, otherwise the argument is undefined. Okay, so things get a little bit tricky when you talk about the angle. The angle here, little arg, this angle right here is not unique, right? Because you can add integer multiples of 2 pi and still get the same angle. So for that reason, we will define the principal argument. Okay, the principal argument. So here, the principal argument and principal argument. Argument is little arg of little arg of z. Let me just see what the convention here it is. Sometimes we use a big arg to stand for principal argument. Sometimes we use little arg. What's the convention here? Oh, actually, the principal argument is little arg. Okay. There's one and only one angle, alpha, that satisfies the condition alpha greater than minus pi and less than or equal to big pi. So basically what it says is, if the vector falls on the negative real axis, we treat its principal argument, this is the principal argument. Okay, the principal argument here, yeah. I'll follow the notation by Markushevich. Okay, so you might have seen different notations elsewhere, but basically principal argument is little arg. This is a little bit different from how I used to write things. For example, in Brown and Churchill, big arg is the principal argument, but here little arg is the principal argument. Okay, this is the unique value alpha that satisfies the condition minus pi less than alpha less than or equal to pi. This is called the principal value of the argument, or the principal argument. So the principal argument is denoted as little arg. Okay, so a general argument. So for a general argument, the value is not unique, and we denote that with a big arg. So big arg of z is little arg, little argument of z plus 2 pi k, okay, where k is any integer. Okay, so this is our convention. Okay, principal argument is lowercase, and general argument is uppercase. This is a multiple value. This is in fact the first multiple value function we've seen in the complex analysis, and actually down the road, all the multi-valued functions in complex analysis all have something to do with this angle. Okay, and now we can give the following relations. So if z equals x plus iy, then z modulus is the square root of x plus y squared. We already know that. And the way you write the argument is a little bit tricky. Unlike the modulus, writing the angles is a little bit trickier. So let's see how that's done. So first of all, when x is positive, that is to say, if the vector is in the first or the fourth quadrant, the principal argument is just the arctangent of y over x. This is when if x is positive. So that's the first case. And if x is on the negative quadrant, oh sorry, not on the negative quadrant, on the second or the third quadrant, things are a little bit different. So if x is negative and y is positive, think about that. So here the vector is right here. So according to our convention, the principal argument should be between half pi and pi. Right? Should be between half pi and pi, but the thing is, arctangent only takes values between minus pi and half pi and plus half pi. So we need to do a little bit of adjustment there. So if you just say here, if you calculate the arctan y over x, what angle would you actually get? You would actually get this angle here, because arctan takes values between, as I said, plus or minus half pi. So to get this angle, you would actually need to add pi to it. Right, so it's clear that I just add pi to get that angle. So it's plus pi. And lastly, the last situation is if x is negative and y is also negative, So yeah, be a little bit careful here. I put y greater or equal to 0 here. Let's think about why is that true? Because when y is 0, and this expression obviously evaluates to 0, simply arctan of 0, which is 0, and you add pi, you get pi, which is exactly what we wanted. Right? Our argument is greater than minus pi, less than or equal to pi. And don't ask me why we take this convention. It's completely arbitrary. Okay, it's just a convention. There's nothing deep going on. We decided to not include minus pi and include pi. Okay, it's just a convention. Okay, and last but not least, if the point is here, and so x and y are both negative. In this case, the arctan would give you a positive value. So here we want the arctan to be actually this angle here. So you would have to subtract the usual arctan y over x by pi. So that's the general relation. All right. Okay. So you can also get more relations. The real part of z is the modulo of z times the cosine of the argument. Can be any argument. And also the imaginary part of z is the modulus of z times the sine of the argument. It's just a well-known conversion between polar coordinates and Cartesian coordinates. Okay, so together you can write a complex number z as the z absolute value, or the z modulus, times the cosine of the argument of z plus I times the sine of the argument of z. Okay, this is called the trigonometric form, the trig form of complex number. And whenever we write this, we assume z is non-zero. Okay, because otherwise the angle is not defined. Okay, so more terminologies. I know, right? The first actual lesson on complex variables is kind of boring because you've already seen this stuff a million times already. X plus iy and x minus iy are conjugate. Okay, I'm not here to bore you. I'm just trying to get the obvious stuff out of the way so we can discuss more perhaps non-trivial stuff. Terminologies has to be set straight. So these are conjugates of each other. So that's the geometry of the two numbers. So typically, if you write z equals x plus iy, then z bar denotes the complex conjugate, and z minus x minus iy. Of course, they are symmetric about the real axes. It's the reflection. Right? Okay. So, and of course, they have these properties. Z double bar is just z itself. The conjugate of a conjugate is just itself. And they have the same lengths, obviously. Z bar modulus equals z modulus. And also, so here we have also the angle, right? The principal argument equals the negative of the principal argument of z bar if z is not a negative real. Okay, if z is not a negative real. If z is a negative real, of course, their argument is the same, equals pi. Otherwise, by our convention, argument of z equals minus the argument of z bar equals pi. So as you can see, the negative real is kind of a corner case, and really there's no good reason to make it a special case. I mean, it's just an arbitrary case, that's just by convention only. And later on, when we discuss complex log, the negative real axis is called a branch cut, and there can be other branch cuts. Okay, to make that's a special curve chosen on the complex plane to define a domain so that a multi-valued function is single-valued. That's the purpose of a branch cut. At the end of the day, it is an arbitrary choice, and to get rid of this arbitrary choice would require the notion of a Riemann surface, which we can only study at the very late part of the course. So at this point, okay, we're just going to introduce branch cuts whenever dealing with multiple valuedness. Okay. So these are the fundamental terminologies for the complex number. So let's now see some operations. So this is section 1.2 in Markushevich's text, operations on complex numbers. Addition, multiplication, that sort of stuff. Once again, nothing surprising here. Addition and multiplication of complex numbers are determined by the following relation. So if you have a1 plus ib1, add a2 plus ib2, the result is just a1 plus a2 plus I, b1 plus b2. That's complex addition. So complex addition is just a vector addition. Very straightforward. Okay, so yeah, there you go. That's the diagram here. So yeah, this is this vector stands for the complex number a1 plus ib1. All right, and here this is another complex number, a2 plus ib2, and the result of their sum is just the usual vector sum, like so. So this is c1, all right, this is c2, and this is c1 plus c2. Indeed, complex addition is so simple, right? It's just I mean, historically, this is not well accepted at all, right? This is hard-won intellectual battles, and right now we're just treating them as just obvious operation. But historically, this is still great achievement. Okay, and of course, you can define subtraction. Addition, it satisfies the quote-unquote field axioms from algebra. That is to say, addition, this is addition. Addition is commutative. Addition is commutative. That is c1 plus c2 equals c2 plus c1. And is also associative. Associative, right? This way, you can write things like c1 plus c2 plus c3 without mentioning where the bracket is. The order don't matter, because c1 plus c2 quantity plus c3 is the same as c1 plus c2 plus c3 quantity. Associativity allows us to ignore the bracket. You can just skip that. Okay, and there exists an additive inverse. Sorry, first you need an additive identity. Exists an additive identity which is called 0. So 0 is the additive identity. It satisfies the property that any complex number c plus 0 equals itself, right, equals c itself. Identity. So additive identity is denoted as 0, which is of course just the origin, 0 plus 0i. And for every complex number, there exists it's minus. So basically the additive inverse, there exists additive inverse as well. Additive inverse. Okay. Okay. There's actually one more property that is implicit. Oh yeah, for the information geometry. Yeah, I'm very excited for that as well. Actually, I regret that I couldn't just do that earlier. I figured, you know what, I'll do some more preparation and perhaps I have more stuff to talk about in information geometry. But I figured, actually, I might as well just start it like a week ago or like more, even 2 weeks ago. I will probably still uh, uh, have the same level of confusion, so might as well just start it that early. Anyway, so tomorrow, yeah, it will be interesting. It'll be interesting. So information geometry. I don't pretend to be an expert or any kind, but we'll walk through some of the basic ideas and see. Just like how we do the usual seminar style streams. And I can already tell because in my old videos on, for example, some of the stats video, some viewers they're already well known. They're already well versed in information geometry, and I actually hope to get some of their feedback too. So yeah, don't expect anything earth-shattering from tomorrow. That's the bottom line. That's my disclaimer. But I'll do my best, and we'll see if there's enough interest for me to do this at a kind of semi-regular basis. But we will prioritize the fundamentals first. Information geometry, despite its age, it's almost a century old. Okay, it's not that new. It's almost a century old. To this day, it is still somewhat niche. It's still not yet mainstream, and we'll discuss why tomorrow as well. So this is C1 and C2. So we will define subtraction. Right? Subtraction, once again, is just the usual vector subtraction. This is A1 plus IB1, A2 plus IB2, and you have this subtraction going on. The difference vector, so this is C1 minus C2. Oh, I forgot to mention that there is an implicit property that addition is also closed. It's not just commutative, associative, and whatnot. So these are actually there's a property that comes even before that. It is closed. You do addition in a set of complex number, you still get a complex number. So that's closed. It's closed in C. Okay. So that's addition. And now we have multiplication. And of course, for multiplication, really? Oh, never heard of the information geometry before me. Okay. Yes, summing up is a commutative group, exactly. It is a group under addition. So multiplication, yeah, exactly, because the Wendelin, the fact that you never heard of it is, I think it has to do with the fact that it's still to this day kind of niche, information geometry. Okay, it's because the models in statistics, machine learning don't always conform to the nice structure of differential geometry. And it's also, there's a cultural issue because people who are trained in stats, machine learning, usually aren't geometers. They lack the vocabulary. Most of them, including myself, aren't well versed in differential geometry. Okay, and people who traditionally well versed in differential geometry aren't particularly well versed in stats and machine learning either. Two biggest group of, perhaps other than pure mathematician who works as geometers. The other group of people who uses differential geometry a lot are theoretical physicists. And they, for the most part, as far as I know, don't seem to care too much about statistics and machine learning, although that's been changing nowadays. Yeah. So, yeah, exactly, Steve, you're completely right. It is a commutative ring. It's also a field. It's a vector space over itself as well as over R. Yeah, totally. This nice thing is if you treat it as a vector space, you have to specify what sort of scalar you're using for the scalar multiplication. If you use C as a scalar, then the vector field, vector space, not vector field, vector space is one-dimensional. If you use R, then as a scalar, underlying scalar of the vector space, if you treat C as a real vector space, then it's two-dimensional. Heck, you can even choose the rationals as the underlying scalar field, in which case the dimension is infinite. But that's rarely used in practice. So for multiplication, we use the following formula: A1, A2 minus B1, B2 plus I, A1, B1 plus A2, B1. So that's multiplication. Of course, there's no need to memorize this formula because this formula was simply a codification of the rule I squared equals minus 1. You just need to know, oh, I squared equals minus 1 and just expand the usual way and you get the right hand side. So that's basically this formula. There you go. Okay. Expand that. You get A1, A2 plus A1, I, B2 plus IB1, A2, and then plus IB1, IB2. Okay, and we assume that the multiplication when I is involved is commutative. You can put I wherever you like, and also you can use the rule I squared equals minus 1. So this way the last term is a real. So that's just A1, A2 minus B1, B2 plus I, A1, B2 plus B1, A2, B1. So that's the formula. So basically there's no need to memorize this multiplication formula. It was designed with the rule I squared equals minus 1 in mind. So that's the rule here. Okay, and the definition of multiplication has several immediate consequences as well. You can easily verify them, which I'll not do because they're just straightforward application, straightforward computation. A multiplication is also closed in C. It is commutative. So it is what we call a commutative algebra, actually. C is an example of a commutative algebra, and it's also associative. There exists something called a multiplicative identity. The multiplicative identity is what we call 1. So 1 is a special complex number such that 1 times a complex number C, any complex number C, equals C itself. And of course, that's just the real number 1, or the complex number 1 plus I0, same thing. And also, there exists a multiplicative inverse for any non-zero. For any C non-zero. Yes, it's also a group. Yeah, it's also an abelian group. There's so much structure going on with C. Commutative group. Indeed. There's so much structure going on with C. And very soon we'll see the geometric meaning of multiplication. Right here we've seen addition has the geometric meaning of just regular vector addition. And multiplication, as we shall see very soon, has to do with rotation. And this is something that is not usually that is not come by default. That doesn't come by default with the usual R2, right? The plane vector space R2. In linear algebra, doing rotation is, I would say, isn't impossible, but it's rather inefficient. In linear algebra, to do rotation, you would have to introduce the rotation matrix. Okay, so the rotation. Oh, thank you very much. Thank you very much for your gift, Steve. You've been so generous. Thanks a lot. So I was saying that in just regular linear algebra, to do rotation, you would need to define the rotation matrix. So the 2x2 matrix. And for complex numbers, rotation just comes with multiplication. It's a really efficient way to encode rotation, as we shall see very soon. Yeah, as I was saying, these are the definitions of addition and multiplication of complex numbers. Subtraction and division are the corresponding inverse operations. Right? Subtraction is defined through adding the additive inverse, and division is defined via multiplying the multiplicative inverse, multiplying the reciprocal. Right? We know addition and multiplication obey the commutative and associative laws. Multiplication obeys also the distributive law with respect to addition. So there's one more property here on the side. Addition and multiplication together is distributive, or shall we say, it's perhaps more appropriately phrased as multiplication is distributive over addition. Just basically the usual algebra rules in arithmetic works here. Yeah. Complex analysis is well known to me. That's awesome. That's awesome. This is one of the most beautiful branches of mathematics, in my opinion. I know a lot of pure math folks, they like to champion the number theory as the most beautiful branch of math. In my opinion, it's complex analysis. That's my opinion. Of course, this sort of thing is subjective, right? But I think complex analysis is the most surprising. And beautiful. And of course, at certain point, complex analysis is used in number theory, right? Analytic number theory. Awesome. So the product of two complex numbers is 0, if and only if at least one of them is 0. So let's prove this, shall we? Theorem. Say C1, C2 equals 0 if and only if C1 equals 0 or C2 equals 0. Okay, so how do we prove this from the definition? So just from this, okay, just from the definition of multiplication, can we prove it? For this sort of statement, obviously the other direction is trivial. If C1 and C2, if one of them is 0, then the product is 0. This is obvious. This is obvious. So what really needs to be shown is the forward direction. So let's assume the product is 0. Assume C1 times C2 is 0. How can we derive C1 is 0 or C2 is 0? A way to actually, I should do another introduction to proof session soon. But basically, if you want to prove an OR statement, here's the common strategy. You negate one of them and show the other must be true. So that's an efficient way to prove, one of the efficient ways to prove OR statement. So you can assume, right, assume the hypothesis and assume, say, C1 is non-zero. And we need to show C2 is 0. And this, of course, if done, will of course prove this statement. So that's just common strategy to prove OR statement. Okay. All right. So here we have C1, C2 equals 0. Can we express, say, C1 plus C2, let's play some game with this expression. C1 plus C2 equals 0 would equal, C1 plus C2 quantity squared would be C1 squared plus 2C1 C2 plus C2 squared. Okay, and C1 times C2 is 0, so this is just C1 squared plus C2 squared. Okay. So here, C1 is assumed to be non-zero. We need to show C2 is 0. How can we do that? Just using the basic properties. I know if you use modulus, it is completely trivial, but I want to use the most basic property. Actually, you know what? Let's not try to be clever and play with identities. Let's just start with the definition. Okay, so write C1 equals A1 plus IB1. C2 equals A2 plus IB2. So C1, C2 equals 0 by the multiplication formula. It just means that A1, A2 minus B1, B2 is 0. And actually here there's a mistake going. This mistake is A1, B2, my bad. A1, B2 plus A2, B1 is 0. Okay. So we have those two equations, and C1 is non-zero. C1 is non-zero. That means at least one of the components in C1, A1 or B1, is non-zero. So we have two cases. So case 1 is A1 is non-zero. Case 2 would be A1 is 0. So when we write cases, we want to make sure the cases are mutually exclusive. So here, what do we need? We need C2 0. We need C2 equals 0. Okay, so A1 is non-zero. We can get an expression between, we can express A2, we can write, from the first equation we can write A2 equals B1, B2 over A1. Over A1. So I mean, I'm actually going to write it this way, B1 over A1 times B2, right? In this case, so A1 is non-zero. So, and now we can substitute it into the second equation. So this way, A1 B2 plus A2 B1. A2, we already have that. So A2 is just B1 over A1 times B2, and then times B1. Okay, this is 0, and we can simplify. You get a1 at the bottom, a1 squared plus b1 squared times b2 equals 0. But we know since c1 is non-zero, a1 squared plus b1 squared is non-zero. This is non-zero, and a1 is also non-zero. This must mean that b2 is 0. Since b2 is 0, therefore a2 is 0. And as a result, c2 is 0. So that's the first case, done. In the second case, when a1 is 0, then from the first equation immediately we have b1, b2 is 0. But because a1 is already 0, b1 can't be 0. Otherwise, c1 would be 0. So since b1 is non-zero, you would have b2 equals 0. Okay, so from b2 equals 0, and from the second equation, b2 equals 0, from the second equation, you just a2 b1 is 0. But once again, as we said, b1 is non-zero, so a2 is 0. So a2 and b2 are both 0, therefore c is 0, again in this case. So this is proved. Okay, so this is actually a nice problem. I might include this in my intro to proof on as an example of proving OR statement. Basically, you negate one proposition, taking the OR operation, and you want to prove the other one. Okay. Ramanujan rocks, exactly. Genius. What else can I say? Has everyone seen the movie about Ramanujan? The Man Who Knew Infinity? I strongly recommend it. There aren't too many movies about mathematicians. There's one depicting John Nash, The Beautiful Mind. Ramanujan this movie was another one. And also Hidden Figures. Not for any particular mathematician per se, but for a group, right? The women who worked for NASA. Unsung hero of the space race. I wish someday they make a movie about Galois, which is really needed in my opinion. I wish one day they make a movie about Galois. It's so dramatic, man. Like math, Galois' life is, and it's also in this turbulent period of French history. And Galois was deeply involved in politics as well. He's also very, so to say, a very has a very volatile personality. These are all great ingredients for a biopic. I don't know why they still haven't made a movie about Galois yet. Yeah, they should do so. And perhaps, Grothendieck as well. Grothendieck. The problem, I guess, with Grothendieck was that his research was so esoteric that it would have problem finding a general audience, right? Think about it. So, Ramanujan's genius was about all kinds of crazy identities, numbers, patterns he found, right? Out of pure intuition, so there's a very romantic aspect to that, right? And also Hidden Figures, of course, its title is entangled with the space race and also women in science. So these are all topics that can struck a chord. Are you going to do Mobius transformation? Yeah, at some point. Yeah, when we talk about hi Leo, thank you very much. I was talking about the lack of a movie about Galois is really puzzling to me. The thing is, Galois' problem is easy to state, right? the polynomial, pretty much anybody with a high school education knows what problem Galois is trying to solve, right? A quintic polynomial and has no roots formula in general, right? So the thing is, for Grothendieck, I mean, of course, he had a legendary life, but it's so difficult to explain what he was working on. Like even among mathematicians, I would say, if let's say if you're now not an algebraist, well, I'm not one, I would have a hard time trying to comprehend what he was working on, right? But of course, the thing is, perhaps you can make the case that you can make a movie for the Bourbaki group as a whole. The story for that would be rather interesting. You can select representatives from the Bourbaki group and tell the story about that group. Because it is not just a project. The Bourbaki project wasn't just purely mathematical, even though the output was. It was also historical and, dare I say, geopolitical. It has to do with a historical rival between France and Germany. So actually, if I'm not making this up. So let me find the Google page for Bourbaki. So the thing is, Bourbaki group started as a response to the development in Germany. How Hilbert's program and set theory-based mathematics became the dominant, so to say, formalization. So here, Bourbaki group. Basically, what happened is France lost a lot of people during the First World War. And Germany, however, on the other hand, during the war, protected its own intellectual class. A lot of French mathematicians, young French mathematicians, died during the First World War. Bourbaki was founded in response to the effect of the First World War, which caused the death of a generation of French mathematicians. As a result, young university instructors were forced to use dated text. While teaching at the University of Strasbourg, Henri Cartan complained to his colleague André Weil of the inadequacy of available course material, which promoted Weil to propose meeting with others in Paris to collectively write a modern analysis textbook. So you got all these people, including, well, Dieudonné. Perhaps Dieudonné would make a good movie, and Weil. Others participated briefly during the group's early year, and the membership has changed gradually over years. But basically, there's a nice picture going on here. This fellow right here, Gaston Julia, the person who invented the Julia set in fractal geometry. Yeah, a pioneer in the fractal, lost his nose during the war. So France, during the Great War, during the First World War, largely exempted no one when it comes to conscription. It doesn't matter your level of education, you got to serve the military. On the other hand, Germany, here he says, Bourbaki founder, Weil, remarked in his memoir, Apprenticeship in Mathematics, that France and Germany took different approaches with their intelligentsia during the war. While Germany protected its young students and scientists, France instead committed them to the front, owing to the French culture of egalitarianism. So these young fellows, they were worried that France was falling behind. It wasn't just about mathematics for its own sake. It also has to do with institutional prestige. That the fact that France as a mathematical superpower was threatened by the development in Germany. So they figured, okay, if the Germans are doing it, we have to do it better. Yeah, exactly. So that's so it's not just a so I mean, of course, the project itself is pure mathematics, but the original motivation and also has to do with national and institutional pride. But we all know what happened later in Germany. Germany basically screwed itself over. after the rise of Nazis, a lot of German mathematicians had to flee the country, or actually, some people even tragically died, including Hausdorff. So basically, Germany shoot itself in the foot. Who knew um, that would happen, right? They have Bourbaki lectures every Friday in IHP in France now. Oh, nice. That's nice, exactly. And math is the crux of a lot of technical fields which are very important for national defense, economic well-being, etc. Well, but I would say in the continental Europe, pure math separated itself as a separate discipline, as a separate endeavor, much earlier than, say, in England, in the UK. So I think those people, the fellows here, Cartan, Dieudonné, etc., they aren't particularly concerned with how to use math to advance France in the field of technology. They just want France to be the best, to have the best pure mathematician. That was their primary objective. So the project of Bourbaki, in my opinion, is worth its own movie because it has all this historical background going on, like all the dramatic event that happened during the Great War, the loss of a generation of young mathematicians. So these are great stories. I mean, it's very tragic, but it's a great project to showcase how mathematicians interact with their home country. Doing mathematics not just for the subject itself, but also from a sense of pride, from a patriotism. Yeah, government interest in bolstering those things. Yes, definitely. Definitely. I'm not quite sure about France. I'm not sure whether Bourbaki was supported by the government or any kind. Um, but definitely. But definitely. Well, in the other countries, perhaps especially in the U.S. and in the Soviet Union, mathematical research was hugely funded by the government. Perhaps the same with France too, but perhaps to a lesser degree. Anyway, we digress. I just hope, bottom line is, we hope to have more movies about mathematicians. It's really, it helps break the stereotype that math has nothing to do with anything else. Okay, it's just kind of do its own thing. No, it's actually very connected with just human history in general, not just the history of math, but human history in general. Um, anyway, so there's that. Very recent story. And also I was talking about the Luzin event. The Luzin event had happened during the Soviet Union. Right? So Luzin was the head of the Moscow school. But because he was associated, well, he was associated with his PhD advisor, who was very religious, and later on got prosecuted during Stalin's Great Terror. And after that event, pretty much all Soviet mathematicians only write in Russian only, and which created this barrier, this kind of self-imposed barrier with the rest of the mathematical community. It's a great story, and because perhaps no less dramatic than what we're seeing here. History of math content. Yeah, I mean, I wish. Perhaps we could do, yeah. Because, guys, you know what? I always find histories fascinating, but at the same time, I'm afraid of not knowing what I'm talking about, right? Because proving a historical fact is much harder, actually, than proving a mathematical fact. Because you got to verify all kinds of sources to ensure a certain event actually happened, and not just your own interpretation. Whereas math, well, if you found a proof, then yeah, that's you're pretty sure that's true. Yeah. Thanks, Leo, for encouragement. So here we also have another property of the complex multiplication, which is also quite important. I mean, we will use it a lot. So the norm, or the modulus of a complex number, is the square root of c times c bar. Okay, and the proof is very easy. So C, if we write C equals x plus iy, then the modulus of C is the square root of x squared plus iy plus y squared. And of course, using the formula for what is called the difference of difference in squares. Yeah, so that's x plus iy times x minus iy, and this is just the square root of c times c bar. One of my historical anecdotes I got verified by someone who was actually there from my last video. That is, yeah, I mean, the thing is, I try to put like verifiable historical anecdotes, and perhaps sometimes not anecdote, but actual mathematical anecdotes, perhaps not just anecdote about mathematician, into my videos, like the fuel between Gauss and Legendre over the discovery of the least square method. You know what? As an Asian person, I always find it so amusing that the Europeans were fighting for priorities like that. How many things were discovered in other parts of the world, in Asia, in the Middle East, in Asia, by the Chinese, Japanese, and Indian mathematicians before the Europeans, and they were fighting for priorities, like as if the naming system isn't Eurocentric enough already. Like, I always find it funny. They keep doing that with themselves. But then again, this is just human nature, I suppose. So the bottom line is, being a mathematician doesn't save your soul, okay? You can still be petty, you can still be egotistic, you can still be cruel to your colleagues, and which is pretty much what Gauss did to Legendre, because he had no reason to behave that way, right? Because speaking of his original contribution to Legendre, his contribution was actually, objectively deeper. He might not be the first one. He may have been. He may have been the first to discover the method, but he decided not to publish. And quite objectively speaking, his contribution to the method of least square was a lot deeper than Legendre. So he could simply let Legendre take the credit of first discovering the method, and he will still get credit. Gauss would still get massive credit for connection to probability, to recursive least squares, things like that. But he decided, nope, it's mine. It's mine from the start, and he just decided to publish it. I decided to keep it because I wanted to make it perfect. What a jerk, man. Yeah. It was their personal glory. I know, right? So, from our perspective, it's kind of silly that they're fighting for this sort of priorities, right? Like the Pascal triangle was discovered in the Song Dynasty in China, like 600 years ago or something like that, and we we just kind of ignore it. Okay, whatever you want to call it, Pascal triangle, we're gonna fight you. We're not gonna fight you. Okay, we're called in Chinese we say Yang Hui Sanjiao. It means Yang Hui's triangle. So Yang Hui was a mathematician and scientist during the Song Dynasty, around the 10th century or so, and that's the standard terminology in Chinese mathematics. The Chinese didn't decide. Okay, we're gonna make an international case that this should be called the Yang Hui triangle. Yeah, you guys want to call it Pascal triangle? Go ahead, have fun with yourself. The credit goes to India, not the religion. I see. Anyway, so here, this is a simple. This is a simple corollary, but now we'll do another important inequality. This is perhaps the most important inequality. Yeah, Hindu is also. Is it Hindi or Hindu, Steve? Is Hindu a language, or Hindi is a language? Okay. So the next important theorem is called the triangle inequality. Arguably the most important, the most common, okay, inequality in analysis. Right. So the triangle inequality says this. Now handy, yeah. So C1 plus C2 absolute value is less than or equal to C1 absolute value plus C2 absolute value, or modulus. Okay. So that's the triangle inequality. And of course, here we have the picture. And from the picture, it's obvious, but our interest is to prove this using complex method alone. Okay, no reference to things like the Cauchy-Schwarz, the real the real inner product on the R2. We don't want to use those things. Of course, you can deduce it from there. It's just a different way to write the triangle inequality in R2. But I wish to use a purely complex method. And there's actually a very cool way to do it. Okay, so how do we go about proving this? So let's first do some scratch work. Or actually, you know what? I figured you can just start from the from here. Okay, to prove the triangle inequality, we're just going to reduce it to a bunch of equivalent form. It is equivalent to show the following. We can square both sides, right? We can square it on both sides, so it's equivalent of proving C1 plus C2 modulus squared less than or equal to C1 modulus plus C2 modulus quantity squared. This is of course equivalent. Okay. And we can use the previous identity, the relationship between modulus and the conjugate, and write this as C1 plus C2 times C1 modulus plus C2 modulus. Actually, well, technically speaking, I should probably show that the conjugate is distribute over addition, but that's a simple exercise. So we won't do that. Okay. Actually, you know what? I think I should. Guys, I'm so sorry. I'm so sorry. Okay. Actually, perhaps we should add a little theorem above. So for C1, C2 in complex numbers, we have C1 plus C2 taking conjugate equals C1 plus C2, even though the proof is rather simple. And also, you can also break the line for multiplication as well. So this one is less trivial. C1 times C2 is C1 bar times C2 bar. Once again, you just evaluate both sides. Okay, this one is slightly less trivial, but you can also easily prove it. So here in the proof of the triangle inequality, so I wanted to do this reverse kind of thinking. Okay, but to do that, you know what I mean. So starting from the conclusion, you want to make sure every step of the manipulation is reversible. So this is sometimes a bit dangerous to do, because often you gotta worry about whether this logic is reversible. And usually when we write this, we write what we're writing here as part of the scratch work. And after you check that the logic is reversible, you write it backward. Of course, there's nothing wrong with that, but I always find it awkward to read, because it doesn't seem to suggest where the proof where the idea of the fruit comes from. Nothing wrong with that when it comes to correctness, but I just find it awkward to read. That's just my personal bias, perhaps. So here I'm just going to write it this way. To prove this is equivalent to prove the following. Okay, so here this is equivalent to expanding the right-hand side, which would be C1 quantity squared plus C1 modulus C2 modulus times 2, and then plus C2 modulus squared. Okay, this is equivalent. Okay, and now let's do something on the left. Okay, now let's do something on the left, and so basically we're going to use this property. You can break the line in the addition. So let's expand both sides separately. So the left-hand side of star just equals C1 plus C2 times C1 plus C2 quantity times C1 bar plus C2 bar. And then we're just going to expand it. You get C1 bar plus C1 C2 bar plus C2 C1 bar, and then plus C2 C2 bar. And this is of course C1 modulus squared. Okay, and the last term would be of course just the last term would be C2 modulus squared. So we assume the multiplicative property of the modulus. No, we're not. Wendelin, we're not assuming C1 C2 modulus equals C1 modulus C2 modulus. No, not complaining. No, I don't think we use that. No, I don't think we use that. Here on the right-hand side, C1 to C2 modulus are just real numbers. So this is just the property of real numbers. Because we're not putting C1 and C2 squared and then taking modulus. We never use this property. Let's briefly check what we actually used. Yeah, it's not used, right? Awesome. Don't be sorry. So here, the last term C2 bar is C2 modulus squared. Okay, and what's going on in the middle? So in the middle, we notice that these two are actually conjugate of each other. We notice that these two are conjugate towards each other, right? So because notice C1, C2 bar taking conjugate, if you use this property, using the distributive property of the conjugate over multiplication, this is just C1 bar times C2 double bar, which is just C2. So these two terms are conjugate of each other. And what happens when you add a number with its conjugate? Okay, let's put these properties here. Properties regarding the conjugate. So these are all simple properties to prove. So 2 times the real part of z, of c, okay, is c plus c bar. Right, this should be obvious because the imaginary part would just cancel. So you're left with twice the real part. So in the middle, you have 2 times the real part of C1, C2 bar. Because these two terms are conjugates. Okay, so that's the right-hand side. And what happened to the left in the, so let's the left-hand side. My bad. So this is just equality. So therefore star, which is equivalent to the triangle inequality, is now equivalent to the following. C1 modulus squared cancels, and C2 modulus squared also cancels. So and 2 also cancels. So it's just equivalent to 2, the real part of C1 C2 bar less than or equal to C1 bar C2 bar. And now, actually, Wendelin, you're completely correct. We're using the multiplicative identity. So here, the fourth one, this one is actually perhaps the least trivial one. We'll come back to 4 in a bit. So C1, C2 multiplication, right? The product of C1, C2 taking modulus is the modulus of C1 times the modulus of C2. Yeah, I remember Leo used, I believe, an identity which is equivalent to this one for a number theory problem. We'll see why in a second, okay? But this seems rather innocent. It seems to be just a direct generalization of the absolute value property. But actually, it's highly non-trivial. This is actually highly non-trivial. We'll see that in a second. But basically, now we're using this property. So if we use 4, now we have this is equivalent of C1, C2 bar less than or equal to C1, C2, C1, C2. Actually, you know what? I'll do it in this way. I'll first change C2 to C2 bar just to match the C2 bar on the left. Okay, and then use the multiplicative property, which is C1, C2 bar. But this is not now obviously true. This is trivial. Since for any C in big C, the real part of C is less than or equal to C modulus. Because C modulus is the square root of the real part of C squared plus the imaginary part of C. You might call this the right triangle inequality. The hypotenuse is greater than one of its legs, any of its legs. So this is trivial, and we're done. Right? So we're reducing the triangle inequality to something obvious. Right? So coming back to 4, right, the multiplicative property for the modulus, this is actually very interesting because this is not obvious. I mean, the proof is straightforward. It's just a computation. The proof is not hard, but that doesn't mean the fact isn't remarkable. So the proof of 4, let's just do that. So C1, C2 modulus is the square root of, is it not the other way around? I write less than or equal to. Yeah, is less than or equal to. Right? It's correct. It's the real part of any complex number C is less than or equal to C modulus. So we're reducing the original triangle inequality to this rather obvious inequality. And every step of the way, the logic is reversible. Okay, so here, coming back to the proof of 4, once again, as I said, proof isn't hard. So you have A1, A2 minus B1, B2 squared, and then plus a1 b2 plus a2 b1 quantity squared, and just expand them. Yeah, brute force expansion. So this is a1 squared, a2 squared, minus 2a1, a2, b1, b2, plus b1 squared, b2 squared, plus a1 squared, b2 squared, plus 2a1, b2, a2, b1, plus a2 squared, b1 squared. All right. Okay, so we want to show, our goal is to show this is the same as the square root of a1 squared plus b1 squared, and then plus b1 squared plus b2 squared quantity, right? So as you can see clearly, the cross term cancel, and we can say for these two terms we can factor out the a1 squared. So let's do that. We got a1 squared, a2 squared plus b2 squared, and next up you got what's up? A b1 squared. Yeah, b1 squared can be factored as you get a2 squared plus b2 squared. So at this point it's now obvious that this is just the square root of a1 squared plus b1 squared, a1 squared plus b1 squared times a2 squared plus b2 squared. So nothing terribly difficult about this one. But it's quite amazing that it's quite amazing that a1, a2 minus b1, b2 quantity squared plus a1, b2 plus a2, b1 quantity squared. If we leave the factorization here, we're not going to bother factorizing this, but rather simply we're going to leave things at this step. And you see this is the sum of four squares. This is a1 times a2 quantity squared plus b1 times b2 quantity squared and a1 b2 quantity squared plus a2 b1 quantity squared. So you can use this identity, okay? So you can use this identity to decompose the sum of two squares into the sum of four squares. I believe this was known, this identity was known already in ancient time. Of course, we're treating, in the context of numbers here, we're treating a1, a2, b1, b2 as integers. I believe Leo featured this identity in one of his earlier streams. So yeah, I made a comment. I was like, oh, this is equivalent to a complex number identity. It's just the distributive property of the modulus over product, right? So yeah, very, very remarkable fact. This is not trivial at all. You can decompose a sum of squares, the sum of two squares into four squares. Not obvious at all. Okay, so the triangle inequality is now proven. This is super important when it comes to the analysis part of the subject, where you want to prove convergence, proving things like the integral exists, that kind of stuff. This is indispensable. And of course, we have the so-called, you have two corollaries, okay? So first corollary is rather simple. Is the triangle inequality for arbitrary number, but finite number of terms. So yes, it is a norm. Yes, it is a norm on C, exactly. It is a norm on C. Steve, you're totally right. To satisfy the norm axioms, you need Yeah, what are the norm axioms? Actually, I'm not quite clear now. Norm, first, I think you need the positivity. Right? Norm is a positivity, also positive definiteness. When norm is 0, the vector is 0, which obviously here the modulus satisfy that property. And so it's just the Euclidean norm, in fact, right? That's just the Euclidean norm. And also, it needs to be homogeneous in a sense that if a complex number is scaled, right? If it is scaled, here the interesting thing is the scalar can be real or complex. In both cases, homogeneity is satisfied. If you scale the complex number, the norm is scaled by the same factor, taking absolute value. And the third one is the triangle inequality. All right. Yeah. No. So Steve, that was actually distance. So you're mistaking norm with distance. What you just wrote, norm of x and y equals norm of y and x, is not actually accurate because norm is a function of one argument. It's like the length of a vector. It takes only one argument, whereas distance takes two arguments. So you can write d of x and y equals d of y and x. That's the symmetry property in distance. Norm can only be defined over vector spaces because when you talk about, no worries, yeah, it's a common confusion here. So norm can only be defined over vector spaces, whereas distance or metric can be defined over more general sets. It doesn't need to have a vector space structure. With that being said, in most applications, the metric spaces encountered in applied mathematics are actually norm spaces. Yeah, given a norm, you have a metric, exactly. Yeah, so of course, not every metric is induced by a norm because a metric don't even have to be defined on a vector space, right? Norm has to be defined on vector spaces. So you have this hierarchy of metric space, include all the norm vector spaces and all the norm vector spaces, and the set of norm vector spaces would include inner product spaces. Yeah, and of course metric spaces are special cases of the topological spaces. So here we're not dealing with the abstract norm. Okay, this is a very well known norm. Right? This is the norm, or the modulus of a complex number is the distance we know since high school. It's very concrete, and pretty much everything we discussed earlier, the inner product, the norm, and the metric, and the topology are all abstractions of the Euclidean space. So here we have the first corollary. So you have C1 plus C2 plus all the way to Cn is less than or equal to C1 absolute value plus C2 absolute value plus all the way to Cn absolute value. So that's an easy application of the triangle inequality for two complex numbers. You just use an induction argument on that, and that will follow. Okay, so so should I do the induction argument here? I think you know what? I'll skip the induction argument, and I will do the introduction to induction formally in the introduction to proof series. Okay, so this is an easy proof by induction by n, induction on n. The base case is n equals 2, is already proved. Induction on n, assume this is true for n equals k, for some k equals for some k greater or equal to 2, and then you prove the inequality is true for n equals k plus 1. Induction hypothesis, yeah, left as an exercise for the viewer. I mean, that's not entirely true because I haven't made a dedicated video or live session on induction. I wanted to do that because it's a powerful technique, even though proving this one is perhaps killing a mosquito with artillery, you know what I'm saying. But this is still like, I want to do the induction later, okay? So yeah, just take my word for granted. You can try on your own, show how to prove you use induction, but we'll do induction formally later. Because induction is also a kind of proof that you can start with an outline. Yeah, we were talking about limit and continuity the other day. I was saying that the dreaded epsilon delta proof actually is quite approachable if you know the structure of the proof. Right? You write down the outline first, and then do the scratch work, and then fill in the blank. That's it. You don't write it linearly from start to finish because that's very difficult. Instead, you start with an outline. Induction proof is another class of proof that can easily start with an outline. So, I mean, I do want to be as thorough as possible, you know, and one of the great advantages of Markushevich is that I find it to be more thorough than some of the Western classics, like Brown and Churchill, and even, what's that called? L4. So it's, Markushevich is very, how should I say, is encyclopedic writer. Even though this is a short course, it still, in my opinion, contains more material than average textbook on complex analysis, which is awesome. Okay, so and another corollary is the so-called reverse triangle inequality. This is also very useful. And let's actually think about how we should prove that. This requires a little bit of a thought. So C1 minus C2 absolute value is greater or equal to the absolute value of C1 absolute value minus C2 absolute value. So how do we prove that? Once again, geometrically, it is obvious, right? Look at the picture. Look at the picture. So if we, look at the picture, let's draw the situation again. Here, say C1 is this, C2 is this. So now we're looking at the length of the Euclid proved the triangle inequality in the plane, right? I know you can prove it using so many methods. You can use linear algebra, and right now I'm just trying to use purely complex method. Or even better, because this is written as a corollary, it should follow quite easily from the OG triangle inequality. How should we do that? Right. You see, in Euclidean geometry, length is a primitive notion. You don't need to define length there. It's treated as the primitive notion, not obvious, but other things are derived from length. And here we're doing something a little bit different, right? So the length is something, addition and multiplication is the primitive, and lengths are derived from them. Okay, so here, let's think about how do we prove that. Usually, it's quite often, well, when it comes to inequality, you would need to do some scratch work. So this would be equivalent to what? This would be equivalent to what? Because here we're saying that the absolute value of a real number, This is C1 norm minus C2 norm, right? That's an absolute value difference. So this is an absolute value of a real number. This is the same as saying C1 C1 norm minus C2 norm modulus is less than or equal to C1 minus C2 absolute value and is greater or equal to minus C1 minus C2 absolute value. This is equivalent to this is what we call the reverse triangle inequality. Okay, let me just give it a name. It's also very, very useful. The reverse triangle inequality. Reverse triangle, okay? So this is a statement equivalent to the original. So can we keep manipulating it? Well, here you actually have two inequalities. You actually have two inequalities, and so let's start from the right one. Shout out to the reverse, I know, right? It gets overshadowed by the big brother triangle inequality, but this is no less useful. So this is equivalent to C1 norm less than or equal to C1 minus C2 absolute value plus C2 absolute value. But we can already see this is true. You can already see this is true because you can simply write C1 as C1 minus C2 and then plus C2. And then you just apply the triangle inequality to the combination of C1 minus C2 and C2. So this side of the inequality is already proven. So I'm talking about this one, okay? This one is equivalent to this one, which is already proven. Just follows from the regular triangle inequality. Can we do something similar here on the left as well? Can we do that? I think we can. So on the left, you have, hold on a second, here. Okay, so let's call this, okay, so let me write this. This is 2. 2 is equivalent to what we just shown. So that's done. What about 1? 1 is what? So I want to put C2 absolute value on the left and C1 absolute value plus C1 minus C2 absolute value like this. Right? And this is also not so difficult to see because you can simply write C2 as C1 plus C2 minus C1 and apply the triangle inequality to this combination. And of course, C2 minus C1 modulus is the same as C1 minus C2 modulus, so this is also shown. Okay, so this is our scratch work. And to write this up, let's write it forward. Okay, so yeah, here's the proof. So let's write apply triangle inequality to here the first combination, which is C1 minus C2 together plus C2. We have C1 minus C2 quantity plus C2 modulus less than or equal to C1 minus C2 modulus plus C2. Okay, so let me just put it this way. Here, this is C1. So this is just C1 modulus. Okay, Oh, here, modulus. And therefore, C1 modulus minus C2 modulus is less than or equal to C1 minus C2 quantity modulus. So that's one side. And apply the triangle inequality, let's call this one. Okay, apply triangle inequality once again to the other combination, which is C2 as C1 plus C2 minus C1 quantity. And we get C2 modulus equals C1 plus C2 minus C1 quantity modulus. This is less than or equal to C1 modulus plus C2 minus C1 modulus. And therefore, here by rearrangement, C1 modulus minus C2 modulus, this is greater or equal to minus C1 minus C2 modulus. And this is 2. Combining 1 and 2, you get C1 modulus minus C2 modulus is less than or equal to C1 minus C2 modulus, greater or equal to minus C1 minus C2 modulus. And of course, therefore, C1 minus C2, the difference between the modulus taking absolute value is less than or equal to C1 minus C2 modulus, and we're done. So that's the corollary, the reverse triangle inequality. So I find it fairly typical that to prove an inequality, you usually start with some kind of scratch work instead of deriving it right on the start, unless there's a super clear clue. Perhaps, I guess, this has to do with the fact that there's usually very little premise in the inequality statement, right? Here, because for example, here the assumption is just that C1 and C2 are complex numbers. Well, what can you say about them, right? How do you say follow your nose and go from C1 and C2 are being complex numbers to this inequality? Typically, I find it much more common to do a lot of scratch work for proving inequality than any other kind of proofs. For other kind of proofs, you can at least, okay, say assume the hypothesis, and then you unpack the definition. You think about what kind of sufficient condition that would lead to your desired conclusion, that kind of stuff. Right? Basically trying to bridge the gap between the hypothesis and the conclusion. But typically for inequality, there's so little hypothesis to use, so you have to solely focus on the conclusion pretty much. For me, it's the draw that makes it easy to understand and write the algebra. You mean the picture? Yeah, of course, exactly. When sometimes you have rather obvious geometric intuition about a result, obviously you should use that and try to formalize the intuition using algebra or analysis, right? That kind of thing. But definitely, yeah, geometry is often a bridge to the actual proof. Okay, so that's the corollary here. And now we can finally interpret multiplication geometrically. So to interpret multiplication geometrically, let's write the complex number in their trig form. Multiplication, geometric meaning. I mean, I've covered this stuff several times on the channel and on live, but just for completeness, I'm going to do it again. So multiplication, geometric meaning. Okay. So here, let's assume C1 and C2 be non-zero. C1, C2 be non-zero. And we're going to use the polar coordinate. Okay, so, or the trig form, same thing. All right. So let's write, say this is Ci. It has modulus Ri, and argument theta I equals 1 and 2. Okay, here I is not the complex unit. Perhaps this is confusing. Let me change that to k. in electrical engineering, people write J for the complex or the imaginary unit, because I can be the current. So yeah, so they use J instead of I. Okay. There's only so many letters. Okay, all right. So we write C1 as R1 cosine of theta 1 times I sine theta 2 quantity, theta 1 quantity. Of course, R1 is the modulus of C, and theta 1 is an argument. Now, remember here, in this very exposition by Markushevich, the big argument, big A, stands for the general argument. It is multiple valued. Okay. All right. So there's that, and C2 is R2. Engineers are severely misguided. And guys, you know what? Steve, the physics dude. Next week we will do some stochastic process for physicists, and over there we will write this as the average of the random variable. This drives mathematicians and statisticians nuts. This is the average of x. Because if you write E of x in physics, E is already big energy. Big E is already energy. And let's say, what if you want to write something like the average energy? You write E of E? This is awkward, right? Just different priorities, man. So I totally get it if physicists wants to use an angle bracket for the average. But this drives mathematicians and statisticians crazy. And statistician has this rule, like of writing random variable as big X, and the realization of the random variable, that is basically the function of the function value of the random variable. Remember, a random variable is a function. It's a function that maps from the sample space to real, right? So statisticians like to write little x for the function value of big X. Okay, to indicate this is non-random. Okay, this is just a function value. Physicists can't be bothered with that sort of thing. They just write big letters, small letter, whatever. To sometimes means the actual observed value, sometimes means the random variable. They can't be bothered. Once again, this drives statisticians completely crazy. This big X, little x convention in statistics is very bureaucratically enforced. So a different tradition. Okay. Personally, I can't stand direct notation, but everyone uses it. Confuses me when I start reading a statistics book. I know, right? This is unfortunate because there's actually I'm going off on a side tangent here, but the thing is, when it comes to a stochastic process, there are extensive literature in both physics and in probability. And the language, as well as even topics, not just the notation, but even topics, are next to mutually unintelligible. It's that bad. Okay, it's not because the results are bad. Okay, statisticians have their priority and their notations. By priority, I mean not just in abstract philosophical sense, but they actually study different things. And physicists, on the other hand, they freely use things like the direct delta function, and all kinds of approximations. Because both statistics, probability, and physics, all of them, they use stochastic process extensively. But the language and as well as the main tool of study are so different. It feels like you're reading something that is completely from a different field. So that's quite interesting. So next week we'll do stochastic processes for physics. I'm not sure whether, say, this will shock a lot of people who follow the channel from the stats side of things. Okay, they'll probably see, wow, physics actually do things a lot different than probability. In probability, so for example, in physics, you rarely even talk about martingale. You don't. I don't think there's a single textbook on by physicists on stochastic process talk about martingales. Or they would just mention it in passing. It's not a primary model. But of course, martingales are a fundamental tool in financial mathematics, stochastic calculus. So it's quite interesting. And also, as I was saying earlier, the difference between the notation in general relativity as well as modern differential geometry. Physicists like to use a lot of indices even to this day. And modern differential geometry has largely moved away from that. So this is why applied mathematics is so important, because we wish to bridge the gap in literature so different researchers from different fields can understand each other. So mathematics can borrow new ideas from applied sciences. New models can learn about new models from applied sciences. And applied sciences can learn from the latest mathematical machinery. And it's very valuable. And sometimes progress are slowed down because of the barrier of entry thing. Okay. Anyway, coming back to the multiplication of complex number and their meaning. So you have C1 times C2. And we just expand things as usual. Okay. So you have R1, R2 cosine theta 1 plus I sine theta 1. Okay. And cosine of theta 2 plus I of sine of theta 2. And you have, just use the regular multiplication formula, you get cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, and plus I, okay, times cosine theta 1, sine of theta 2, plus sine of theta 1, cosine of theta 2. But notice, this is just the trig identity. It's nothing but the trig identity. So you end up getting, as if by miracle, trig identity appears. This is sine of theta 1. Actually, cosine. Cosine of theta 1 minus theta 2. Oh, actually plus. Cosine of theta 1 plus theta 2. My bad. And then plus I, sine of theta 1 times plus theta 2. Yeah, it feels completely magical. I know, right? So somehow introducing I equals square root of minus 1 allows you to recover trigonometry. So feels like complete magic. So basically what happens is that C1, C2, this tells us that C1, C2 has a modulus of R1 times R2, which is C1 modulus times C2 modulus. This is something we've already seen earlier. Right? And the argument of C1 times C2 is the argument of C1 plus argument of C2. Basically, theta 1 plus theta 2. So that's the idea. Let's draw the picture. Okay, this is, say, C1. Length is R1. Angle is theta 1. This is C2. Length is R2. Angle is theta 2. After multiplication, you get this new complex number C1 times C2, and the length is R1 times R2. And most importantly, the angle is an addition. So the angle is what? The angle is theta 1 plus theta 2. Brilliant. Awesome. Right. So basically, and now you have, and similarly, immediately you have the other two formulas for the division. So C1 minus theta, C1 over theta 2 is R1 over R2. Right, you can easily derive that. And perhaps I should do it. Perhaps I should do it. So what is 1 over theta? 1 over C2. Right, 1 over C2 is what? 1 over C2 is the multiplicative inverse of C2. So 1 over C2, it should satisfy the property of 1 over C2 times C2 equals 1. Right? So let's write 1 over C2 as, say, rho of cosine of phi plus I sine of phi. Right? First of all, here if we assume C2 is non-zero, therefore its reciprocal exists and cannot be zero. So therefore it should have a trig form. Right? So this way we have 1 over C2 times C2 is what? Using the trig form of this thing times the trig form of C2, you get rho times R2 times the cosine of phi plus theta 2 plus I sine of phi plus theta 2. Okay, so actually, guys, I did not mention something. You can actually prove that the multiplicative inverse is unique. Okay, you can prove the uniqueness of multiplicative inverse from the definition. Actually, guys, let's do that. I think I should do that. Somehow I missed it. Okay. 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 How do I add it? Perhaps. Yeah, I want to prove the uniqueness of multiplicative inverse because this is needed here. Let me just finish this argument real soon, okay? And I'll see why this is needed. So this is 1. This is 1. So obviously, if rho is 1 over R2 and cosine is 1, sine is 0, the equation would be satisfied. Right. So clearly, rho equals 1 over R2 and phi equals minus theta 2 makes the equation true. Makes the equation true. So, and now you can just say, by the uniqueness of multiplicative inverse, you have found 1 over C2. So by the uniqueness of multiplicative inverse, you can simply say 1 over C2 is 1 over rho. And yeah, phi is minus C2, so this is just cosine of minus theta 2 plus I sine of minus theta 2 And of course, you can write it as using the trig identity, the fact that the cosine function is even and the sine function is odd. You can write it this way. Yeah, so you can, so here the uniqueness of multiplicative inverse comes into play. Actually, let me prove it here. It should be more appropriately proved here or here. Okay, apologize. Let me try to make some space for it. Because this is a short course by Markushevich, he did not include the proof. I think it's needed here. The multiplicative okay. Does it work? Yeah, okay, awesome. So this theorem is about division or multiplicative inverse. Same thing. So it says if C is non-zero, okay, if C is non-zero, then there exists a unique 1 over C. There exists a unique complex number, say C prime, such that C prime is 1. And C prime is denoted as 1 over C or C to the minus 1. Okay, so the uniqueness. Existence of uniqueness. There exists a unique C. Well, it's quite straightforward. You just need to solve an equation. So this is the proof. Let C be A plus IB, okay? Such that A squared plus B squared is non-zero. This way C is a non-zero complex number. So now let's assume C prime is x plus iy such that C times C prime equals 1. You can solve for x and y. We can solve for x and y uniquely. And this will establish the existing uniqueness. So what it boils down to is a system of linear equations. So C times C prime equals 1 is the same as ax minus by, right, plus I times ay plus bx, and this equals 1. You want to prove it without using conjugation? Well, I think conjugation is a shortcut. Actually, yeah, thanks very much, Steve. Bye now. So, Vandelin, the reason, I know what you're thinking, right? I think what you mean is C prime is C bar over C bar. You want to do something like this. Of course, you can use it to verify, oh, this is indeed a multiplicative inverse. But how do you show uniqueness then? Right? You just give one example that works. How do you know this is the only one? So what I'm doing is I'm just going to start from the definition, use the multiplication formula, okay, and solve for x and y. As we can see here, what we end up getting is a system of linear equation. This is the same as ax minus by. A and b are treated as constant, x and y are unknown. Okay, ax minus by equals 1. And ax plus by is 0. And so you can use the Cramer's rule or whatever to solve this. So this is the system. This is a system of linear equations in x and y. It has a unique solution since the determinant is non-zero. Determinant is a minus b, ab. Oh, actually my bad. Here it should be bx plus ay. Okay, the determinant is a minus bba. Taking the determinant, you get a squared plus b squared, and that's a non-zero by the assumption. So it has a unique solution, therefore existing uniqueness is now established, basically. And now you can write down the formula. So you can use method of elimination to get the solution. So I'm just going to skip the steps, okay? Elimination or whatever. Use your favorite method to solve system of linear equation. Use matrix or whatever, okay? Gaussian elimination, REF, up to you. But basically x is what? X is a over a squared plus b squared. And y is minus b over a squared plus b squared. You can quickly check this is true. So this finishes the proof. Unique solution is now established, and now you can use a formula to memorize the result, to summarize the result. So 1 over c is c bar over c modulus squared. This is the formula. We often use it in actual calculation, but this should be the actual proof. Because if you just say, oh, let's just try this and see if satisfy the definition of the conjugate, satisfy the definition of the multiplicative inverse, right? You can do that, but this is just one possibility. How do you know that's the unique one, right? So the point is uniqueness. Here we're using the uniqueness to establish the reciprocal formula. Right? Here, by the uniqueness, you just need to pick a row and find that works. Right? So, and after that, you have C1 over C2. It's just C1 times 1 over C2, and therefore it's just, you just add the angle, right? C2, the angle for C2 is minus theta, so this is just R1 over R2. Together, you get cosine of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2. That'll be it. So this is C1 over C2, division. So basically, from this, we can say the norm, the group, the inverse is easy to prove, right? You can, yes. So it's a corollary. You can prove the uniqueness of inverse from the group axioms. You can do that. Yeah, you can do that. So here, I mean, I'm using just the definition of multiplication. So you're totally correct. So in the group, if in a group the uniqueness of inverse is a property, is implied by the axioms. All right. So here we wanted to summarize the result for division. Okay. So yeah, this is C1 over C2 modulus is C1 modulus over C2, so that's nice. So the modulus also distributes over division. Fantastic. And the argument of C1 over C2 is the argument of C1 minus argument of C2. So that's a nice property. Okay, box this one. So I think we can skip the diagram for this one. So the complex multiplication has this nice property. So, yeah. And if we apply these properties, yeah, and if we apply these properties to powers, it makes us very, yeah, nice application of linear algebra to demonstrate it out. Yeah, thanks a lot. So, we're saying that you have here you have powers. So powers works like this. So c to the n. So if c is r cosine of theta plus r sine of theta, then c to the n would just be r to the n cosine of n theta plus I sine of n theta. Okay, there's that. And what else? C to the minus n. C to the minus n, that's 1 over c to the n, is r to the minus n cosine of minus n theta, which is just cosine of n theta, minus I sine of n theta. There you go. Okay. Okay, so and then you can also calculate roots. We will come back to the root calculation after we study the exponential form. So in some books, the exponential form is defined as a symbol. E to the I theta is defined as a symbol. But I think here in the book, the author wanted to introduce exponential form after the exponential function is defined, which in my opinion is perhaps more rigorous. So let's just keep it that way. We will say nothing about the magical formula e to the I theta equals cosine of theta plus I sine theta here. But I did give a motivated definition of this symbol in my video on complex numbers. So you can take that route, but here I'm trying to follow the logical development by the author, so I will not use that here. Okay, so we'll talk about the square root a bit later, but here you can just gonna give the formula. Okay, c of p over q, c over p over q. This is defined as r of p over q. Here p and q are irreducible fraction. Okay, let p and q be integers. Q greater or equal to 0, not equal to 0, q greater or equal to 2. P over q irreducible. Then here, we'll see an example of this. We'll see an example of this and then move on. We'll talk about a more compact version of this later, once we have the exponential form. Okay, so just right now it's just the cosine of what? Of p over q, p over q times theta. Remember, theta can be multiple valued. So in general, the root is also multiple valued. Okay. So let's see an example of the root formula. It's not in the book, but I figured it's perhaps a nice exercise. So let's say we wish to calculate. Let's calculate what? Let's calculate the I to the 2/3. Let's calculate this. So we wish to consider all the possibilities on the right. So first let's convert I to a polar form. Draw a picture for extra clarity. This is I. It's just on the imaginary axis. So what would theta be? Solution. So first let's write I in the polar form or trig form. I is cosine of the angle half pi plus 2k pi. Right. We're considering the multi-valuedness of the angle. Sine of pi over 2 plus 2k pi. Let's write I this way. Okay, so according to our formula, I to the 2/3 power should be what? Of course, r is just 1, so here at the start, out the factor, the modulus is still 1. Nothing's changed. So in the angle department, we want to multiply the angle by 2/3. So multiplying the angle by 2/3, so it's 2/3 times the angle half pi plus 2k pi. And then plus I sine of the angle, same angle, 2/3 times half pi plus 2k pi. Okay, but what is this angle then? Simplify, you get pi over 3 plus 4k pi over 3. Same here. Pi over 3 plus what? Plus 4k pi over 3. So let's draw the diagram, okay? So what's third of a pi? The third of a pi is 60 degrees, like this. Right, k is an integer. K is an integer, so let's consider what are the possibilities here. So this is third of a pi. So if you add third of a pi by here you got what's 5 pi over 3? 5 pi over 3 is 2 pi over 3 plus pi. 2 pi over 3 is this, huh? No, 2 pi over 3 is this. It's like this. Yeah, that's like 2 pi minus pi over 3. So this is 5 pi over 3. Yeah. You just draw the angles to make it super clear. I just wanted to see how many distinct values are in here. Okay, that's my objective. So here you have third pi, 5 pi over 3. Okay, so that's when k equals 1. Okay, let me write that. This is k equals 1. What about k equals minus 1 then? So k equals minus 1. That's a minus pi. That's a minus pi, so it's here. K equals minus 1. So k equals -1 gives you just minus pi. This is minus pi. Okay. And if we try other values, let's say k equals 2. K equals 2 becomes this angle again. So there are 3 distinct values basically. Only 3 distinct values. That's it. So these 3 values, and we can just read them off from the diagram. And remember, they all lie on the unit circle because the radius is always 1. So therefore, you got -1, which is this point. And when k equals 0, that's cosine of pi over 3. That's 1/2 plus I square root of 3 over 2 and minus 1/2. Oh, not minus, just plus. You have 3 values, distinct values here. Minus I square root of 3 over 2. That's it. So you have 3 distinct values. Even though here k can be any integer, because of periodicity, there's actually only 3 distinct values. That's a nice example, in my opinion. Right. So therefore, we summarize in this root formula. So how do you obtain these values? So you can just fix one value of the original argument, fix one theta argument, right? And then you on the right hand side for the hang on a second. So yeah, so my point is to obtain these values, you can use this kind of a rotation strategy. So fix one value of the argument. Let's call it phi. And then replace phi by phi plus 2 pi, phi plus 4 pi, etc. Substitute phi plus 2 pi, etc. all the way to phi plus q minus 1. Q minus 1, 2 pi. The point is, the denominator is p. The denominator is q, okay? The denominator is q, and the fraction is irreducible. There should be q distinct values. Here you have 3 distinct values. In general, you should have q distinct values for getting this formula. Okay, later on when we have the exponential form, there are more efficient way to express this. But basically, there should be q distinct values for the power c to the p over q. Okay, that's cool. So so far we've done just the basic calculations, right? The geometric interpretation, the basic calculation for complex numbers, and we proved some important results. Hang on a second, what the hell is this? Oh no, something is terribly messed up here. Okay, so yeah, I think when I moved it, the you see the yeah, so it's okay. The things got mixed up. Let me fix that, okay? Let me fix that real quick. Theorem. Always hate it when it happens. Sometimes this is sometimes it makes you prefer things like MS Word, or I don't even know what the heck this is. Sometimes this makes you prefer things like MS Word or LaTeX. Yeah, but for streaming, perhaps MS Word is better. Okay? I just want to do things in an old-fashioned way, if you may. Um, it gives me the most freedom. Okay, and if I want to write something, I can just do it wherever I want. Anyway, so now let's talk about the limits, right? So this is already very similar to our definition of the limit in the Zorich episode. So here, next section, 1.3, the limit of a sequence. So this is a crucial tool for discussing topology of the complex plane. And I think we're probably going to use some results from real analysis without proving it. Okay. So guys, let me just grab some water. We'll be back in a minute. All right. Um, Now I'm back. So we wish to define the limit of a sequence, and the definition is very similar to, pretty much identical to the definition of limit in real analysis. So we say a sequence of complex numbers which is Cn equals An plus Ibn, this sequence of complex numbers, is said to converge. Is said to converge to a limit if it satisfies the following condition. It was less than a minute. Okay. Anyway, yeah. The water dispenser is right next to me. So yeah, the sequence of complex number is said to converge to a limit. And let's write the limit as just C equals A plus IB. If if for every positive number epsilon, so this epsilon is a real number, real positive number, there exists a positive integer equals 1, 2, and so on, such that for all n greater than big N epsilon, big N of epsilon, because big N may depend on epsilon, okay? You have the following. That is Cn minus C absolute value is less than epsilon. Okay, so let's draw a picture. So this is a complex plane. and this is C. You see, let's draw a circle with radius epsilon. So this is what we call a neighborhood of C, or epsilon neighborhood of C. Okay, it says for every such epsilon, the tail of the sequence, starting from index big N plus 1, is completely contained in the neighborhood. So outside of the neighborhood, there can be only finitely many sequence members. So let's draw that. So these are the points in this sequence. These are all but finitely many members of the sequence. So here, this is Cn plus 1, Cn plus 2, and so on. Okay, there still might be other, say, for example, it's still possible for a member C in the sequence, a member Cn in the sequence, where little n is less than big N, to be inside the interval, or sorry, to be inside the neighborhood. It is possible for that to happen, but we don't care. What we care about is after a certain threshold, everything in there is inside the neighborhood. What happens when little n is less than or equal to big N? We simply don't care. Okay, so this can be reformulated in many ways. There might be points outside, but we don't care. So if we rephrase this in a purely verbal fashion, no notation whatsoever, okay? Basically, it means that every neighborhood, this is equivalent of saying every neighborhood of C contains all but finitely many members of the sequence. Cn. So that's the definition of limit. Okay. And here you have a theorem, a quite simple theorem, which says that, and okay, actually here you have a notation as well. Notation, we can write the limit of Cn equals C. You can omit n tends to infinity. You can ignore that because the limit of a sequence can only make sense when n tends to infinity. It can't go to minus infinity. It can't go to a finite number either, because if n tends to a finite number, that's just n at that finite number. So it's just evaluation of a sequence member. So it's trivial. So you can just skip n tends to infinity. Okay, don't tell that to freshmen. But there's no loss of information if you write limit of Cn. Okay, and then or you have Cn tends to C. Okay, the theorem says the following. It says the limit of Cn equals C, where Cn is An plus Ibn. An and Bn are both real numbers, okay? Yeah, it is implied. An and Bn are both real numbers. And C equals A plus Ib. This is true if the limit of An is A, and if and only if actually, if and only if the limit of Bn is B. So this is quite intuitive. It basically says a sequence of complex number converges if and only if it converges component-wise. Okay, so let's think about how we prove it. Okay. How do we prove this? Well, so let's start by proving one direction. So yeah, let's prove. So assume you have the limit of Cn equals C. You want to prove component-wise convergence. You need to show the limit of An is A, the limit of Bn is B. Okay. So how do we do that? Well, let's take a look at the picture, shall we? So the idea is this is C, this is Cn. Okay, C equals A and B. Look at the picture. C equals the point A and B. Cn equals the point A and Bn. Cn tends to C. That means the distance between Cn and the C tends to 0. So in this right triangle, it means the both legs tends to 0 as well, because the legs, which is absolute value of An minus A and absolute value of Bn minus B, are both bounded by the hypotenuse. So we're done. So to formally show this, we follow the template of convergence, proving convergence. You write down all the needed quantifiers. So let epsilon be greater than 0. This corresponds to for all epsilon greater than 0. Let epsilon greater than 0. So here we can use the fact that Cn tends to C. Since Cn tends to C, there exists a big N epsilon, which is a positive integer, 1, 2, 3, and so on, such that for all n greater than big N epsilon, Cn minus C absolute value. Here we don't even need the reverse triangle inequality. Here we don't need that. Wendelin, we don't need that here, because An minus A absolute value is already bounded by the absolute value of Cn minus C. Right? So here, since An minus A is just the real part of Cn minus C, we have An minus A absolute value being bounded by Cn minus C absolute value, or the modulus. And thus, for the same big N, for all n greater than big epsilon n, An minus A absolute value is less than epsilon. Just follows from this inequality. And therefore, by definition, An converges to A. And similarly, you can do the same business for Bn. Since Bn minus B is the imaginary part, I will show one example that makes use of the reverse triangle inequality, though. I'll do that in a bit. So here, Bn minus B is just from this diagram. It's very intuitive here. This is less than or equal to Cn minus C as well. So as a result, for every n greater than big N epsilon, Bn minus B, absolute value is less than epsilon. So therefore, by definition, Bn converges to B. So this part is done. Okay, so yeah, the forward direction is done, and now let's do the backward direction. So now let's assume you have component-wise convergence. Assume An converges to A, Bn converges to B. And we wish to show that Cn converges to C. So basically now in the diagram, the two legs tends to 0, right? We want to argue that the hypotenuse also tend to 0. They shouldn't be too difficult, but to make it a formal proof, we need to make sure you pick the epsilon and big N, okay? Just use the definition. Now, right now, we don't have any tools other than the definition. Okay. Yeah, so you need to show that the need to show Cn converges to C. Okay, so how do we cook up a big N, so to say? So the idea is, let epsilon greater than 0, we need to show there exists a big N. And it has to come from the assumption. It has to come from the assumption. So how do we go about doing that? Well, I mean, why don't we just pick, say, we want the hypotenuse to be less than epsilon. Right? And why don't we consider just the right, the right isosceles right triangle. So the two legs would be just epsilon over square root of 2 and epsilon over square root of 2. So the thing is, because An tends to A, Bn tends to B, you can always make the difference between An and A and Bn and B to be arbitrarily small. So let's write it this way. Okay, so let epsilon greater than 0. We're going to pick big N as follows. Pick big N epsilon as the maximum of N1, N2, N1 epsilon, N2 epsilon, okay, where N1 epsilon in 1, 2, 3, and so on is such that for all n greater than big N1 epsilon, A1, An minus A absolute value less than epsilon over square root of 2, and N2 epsilon equals 1, 2, 3, and so on is such that for all n greater than big N2 epsilon, Bn minus B is also less than epsilon over square root of 2. So this way, now suppose you have little n greater than big N epsilon, Okay, suppose that, then what happened? Then Cn minus C absolute value is of course the square root of An minus A absolute value quantity squared plus Bn minus B absolute value quantity squared. This is less than or equal to the square root of half epsilon plus half epsilon squared plus half epsilon squared. And this is just epsilon. So now we have all the ingredients, right? For every epsilon greater than 0, there exists big N epsilon. We picked it. There exists. Suppose little n is greater than big N epsilon. Distance is less than epsilon. So we have all the necessary ingredients in the definition. And therefore, by definition, let's conclude that, by definition, Cn converges to C, and we're done. This completes the proof from both directions. Okay? So therefore, this enables us to apply the theory of sequence of real numbers to sequence of complex numbers. Here, we know that from the theory of real numbers, there is this result called the Cauchy criteria. The Cauchy criteria. Here, you can have a Cauchy criteria for complex number as well, right? We know An and Bn are sequence of real numbers. Sequence of real numbers converge if and only if they are Cauchy. And this is a property of the set of real numbers, the completeness axiom. So now you can just say Cn, the set of complex numbers, converge to C if and only if Cn is Cauchy. Right. So here you can say the entire theory of sequences of real numbers can now be applied. For example, you have the following result, theorem, Cauchy criteria. Okay. Should we review a little bit about what a Cauchy sequence is? Chat, what do you guys think? Should I do a review of Cauchy sequence in general? Here the Cauchy criteria says the limit of Cn, or should we say the limit of Cn exists, aka Cn converges, if and only if Cn is Cauchy, or is a Cauchy sequence. Any input, chat? Do you want me to review the basics of Cauchy sequence? Can do that. For every epsilon greater than 0, there exists big N epsilon equals 1, 2, and so on. Yeah, at least the definition is in order. Yeah, here I'm writing the definition. For you have Cm, okay, for all m and n greater than big N epsilon, Cm minus Cn absolute value is less than epsilon. Well, we reviewed the definition of a Cauchy sequence in our measure theory live, but here I'm just going to pretty much repeat myself and do a review of Cauchy sequence. Yeah, proving this is not easy. Okay, proving the Cauchy sequence, proving the Cauchy criteria is not easy in the set of real numbers, because one direction is easy. If a sequence is convergent, you can immediately prove it is Cauchy. However, to get the other direction, you need some kind of statement regarding the completeness of R. For example, the Bolzano-Weierstrass theorem to get the convergence going. So I'm not going to prove the Cauchy criteria in the real case, but rather I'm just going to emphasize what this means, okay? What the definition of Cauchy sequence really says. Cauchy sequence are exactly the sequences whose tail diameter tends to 0. Okay, so this is a review. There's a bunch of equivalent ways to describe Cauchy sequences. Equivalent formulation. Cauchy sequences. So here the definition applies to both real and complex sequences. 1. A sequence is Cauchy, Cn is Cauchy, if the tail diameter tends to 0. And what do we mean by tail diameter? It's the diameter, okay, of the set Cn, Cn plus 1, and so on, defined as follows. This tends to 0. Okay, let me just write it this way. This tends to 0 as n tends to infinity, and where a diameter of a set is defined as follows. So the diameter for a set say A, which can be a subset of R or a subset of C. The diameter of a set A, this is defined as the supremum of values x minus y absolute value such that x and y are in A. Okay, so here's the diagram. So this is the set A, and just pick an arbitrary pair of point x and y and you calculate their distance. If it's real, it's just the absolute value. If it's complex, then it's the modulus. The sup of the distance is called the diameter. You're picking essentially the length of the longest chord. The diameter of the tail of the sequence tends to 0. Then the sequence is Cauchy. Okay, and the second equivalent formulation is as follows. Cn is Cauchy if say you can for every every n and every k equals 1, 2, and so on, Cn plus k minus Cn absolute value, Cn minus Ck minus Cn absolute value is less than or equal to some An for some sequence An of real numbers such that An tends to 0. So that's saying that the the distance between elements in the sequence can be bounded by another sequence that tends to 0. Here, the key is that this is true for arbitrary k. For every n, for every fixed n, this is true for arbitrary k. So it doesn't matter how far you go down the list. So you start from Cn. It doesn't matter how far you go down the list. The distance between Cn plus k and Cn is always bounded by An. So it's a nice exercise to show that the OG definition of a Cauchy sequence is equivalent to both 1 and 2. It's straightforward to show them. Yeah, let's take the completeness of R for granted, then C is easy to show. Yeah, and C is also complete. In fact, Rn is complete due to R is complete, right? Actually, I'm not going to prove this result. I'm just going to state it, right? Because and emphasize this is the definition of the Cauchy sequence. In general, the notion of Cauchiness and convergence are not the same, because you can still talk about Cauchy sequence in the set of rational numbers, but in rational numbers, Cauchy sequence aren't necessarily convergent, because if you're only considering rational numbers as your whole universe, then the Cauchy sequence in the rational numbers may not have a limit in the set of rational numbers. So that's an important distinction. In the discussion of limit, right, you're always comparing the distance between the sequence member, Cn, and the proposed limit. So the C here is an object external to the sequence. In the definition of Cauchy sequence, however, you're only comparing the distance among members themselves. So this always makes sense regardless whether the limit exists. It is a property of the real numbers that whenever a sequence is Cauchy, it has a limit. That's called the completeness. It's not true for an arbitrary set. Okay, and in fact, let's give an example. One of the Cauchy sequence, perhaps the Cauchy sequence that we use literally on an everyday basis, is what? Is decimal expansion. Right. Example, decimal expansion is a Cauchy sequence. You can think of decimal expansion as a Cauchy sequence. This underlies the practice of using decimal expansion to represent real numbers. Viewed as a Cauchy sequence. Why is that? Why is that? Well, so let's take d equals 10. So the decimal expansion, infinite decimal expansion, big N, say big N dot, big N is the integer part of the whole number part of the real number. D1, D2, D3, and so on, keeps on going. This decimal expansion can be viewed as a sequence. As a sequence, let's call it AN, where A naught is big N, just the whole part, just the whole number part. This is A naught. What is A1? Well, A1, you guessed it, is N plus D1 over D. Oh, actually, I forgot to mention d1, d2, and so on are integers among 0, 1, all the way to 9, or d minus 1. Because this analysis can really be applied to any arbitrary base expansion. You can set d equals to 2 and you get the binary expansion. And the argument is essentially the same. In the binary expansion, you still have a Cauchy sequence, as we shall show. Okay, so here where d1, d2, d3, and so on, they all belong to the set 0, 1, 2, all the way to d minus 1. Okay, so here the sequence looks like this. This is A0, it's just big N. Here A1 is big N plus D1 over D. Well, what's A2? A2 is N plus D1 over D. That's basically A1 plus an extra digit. That's D2. D2 over what? Over D squared. And in general, A little n is what? Is n plus D1 over D plus all the way to dn over d to the n. And it keeps on going. So this is an. This is an, all right? So can we say, how can we show this is Cauchy? We claim that this sequence an is Cauchy. This is actually a very nice exercise. Claim an is Cauchy. Let's do that. We're going to actually use the third definition here, this definition. So let n and k to be 1, 2, and 3 fixed. Okay. And fixed. So let's consider the difference of an plus k minus an. And of course, we know the difference between the two are the digits that comes after an. So an stops at the digit dn, right? So the next digit that is missing is dn plus 1 over d to the n. d to the n plus 1, sorry. d to the n plus 1. And plus all the way to here. This is the absolute value. Because big M might be negative. So the difference can be negative. That's why we take the absolute value. And here, finally, you have dn plus k. Yeah, dn plus k over d to the n plus k. So we can bound this. Each digit di is less than or equal to d minus 1. So we can write all of them is here, all of them is less than d minus 1. So let's take out the d minus 1. And you also have the common factor of d to the n. And now this is what? This is 1 over d. Actually, let's do this instead. Let's take out the common factor, 1 over d to the n plus 1, and you get 1 plus all the way to 1 over d to the k minus 1. There are k terms here, but as you can see, this is a finite geometric sum. But we can say this is less than the infinite geometric sum, which is the sum of d to the minus 1 to the power of m. M goes from 0 to infinity. Okay, here this goes from m goes from 0 to k minus 1, but this is less than infinite sum. And we can use the geometric sum formula. This feels like a measure series stream because we use a lot of geometric series there. We use what we call the abusing the Zeno's paradox, right? So here, and this is the 1 over 1 minus 1 over d. Okay, and do the multiplication. So d minus 1 cancels, right? So this is, yeah, this is d minus 1 over d together, so you get 1 over d to the n. And as you can see, this is an upper bound that is independent of k. Here, we said that Cn plus k minus Cn, you should get an upper bound independent of k. This is an upper bound independent of k, which means it's a Cauchy sequence. It doesn't matter how many digits that you omit, right? The difference between an plus k and an will be no greater than this upper bound. So this is a Cauchy by the second formulation. By formulation 2, an is Cauchy. So that's a Cauchy sequence that appears in everyday life, decimal expansion. So now, by the Cauchy criteria, we know this converges to a real number, and that's why real numbers can be seen as decimal expansion. We typically don't define, although it is, I guess it's technically possible, but typically we don't define real numbers as decimal expansion because it feels completely arbitrary, right? This is just one particular form, highly restrictive form of a Cauchy sequence. And the fundamental property of a real number, that is completeness, should not depend on how it is represented. It's kind of like how the situation with tensor analysis, right? When I was doing my tensor stream, like earlier in the part of the stream, like people were yelling at me, and not yelling, but gently reminded me that, oh, you shouldn't use the tensor index notation, you should use a modern index-free notation. I was like, yeah, that's perhaps more clean, but the problem is, how do you make that, say, relevant? How do you make that relevant to applied scientist work? Of course, it ultimately is relevant, but the notation feels too abstract that it's difficult for one to see the immediate relevance, right? That's what I'm trying to say. So that's why I stick to the classical index notation, and now those people probably left the series and no longer had the appetite, right? But anyway, I'm just kidding. So the point is, you can define tensors in terms of its component, right? Using the transformation law, right? You can define tensors that way, but pure mathematicians don't like it because it is okay. Thank you very much, Gwendolyn. You always make me sorry. I mean, this is the time convenient for me. Yeah, thank you very much for staying this late. Actually, I'm going to close the stream really quickly soon because I don't want to talk about the topology of complex plane super late because everybody's tired. You know, I want to, including myself, I want to talk about the topology of complex plane later. Okay, so as I was saying. I defined the tensors using index notation, and people, some mathematically inclined audience reminded me that this is not elegant. I know that. Of course I know that, right? The problem is, how do you make it relevant to applied work, right? If you just give the most abstract definition of tensor right away, tensor product, the dreaded O times symbol, it very soon started to feel like unnecessary abstraction for God knows what is applied to where. So that was my original motivation. So the thing is, here, in principle, you can define a real number in terms of decimal expansion. It is possible. But a more elegant way is to start from the fundamental axioms of real numbers, that is the completeness, and you treat decimal expansion as a particular kind of Cauchy sequence, which converge by the completeness axiom. So by the formulation, AN is a Cauchy sequence. Is a Cauchy sequence. So here I'm just giving an example of a Cauchy sequence. Okay, and we can import the theory of real sequences directly into complex variables, and we conclude that a complex sequence has a limit if and only if it is a Cauchy sequence in a complex sense. Okay, yeah, actually, I'll just close it for now. Let's stop for now, okay? And we will continue next time, probably next Friday. Okay, next Friday, and we'll in particular discuss what do we mean by limit of infinity on the complex plane, as well as sets of points on the complex plane. Important classes of subsets of complex plane. Seems like open set, closed set, compact set, that kind of stuff. Okay. Anyway, I'll close the stream for now, and I'll see you guys next time.